So thank you very much for the introduction. I also want to thank the organizers. So today I'll talk about this. I slightly changed my title from Fourier states to strong coupling states in light coupled Dirac electrons. So today I want to talk about basically two subjects. One is about some relativistic particle like electrons coupled to waves. This wave can be traveling and have some speed. And I will show you that if this speed approaches the speed of this relativistic fermions, there will be some interesting effect, like this supersonic like stuff. Also, actually, so in this workshop, we are talking about many cavity physics. I actually have one paper, like one of my few papers on cavity physics, which is in one-dimensional nanotubes. Okay, so it was published like 3 years ago. So I will try to explain the physics here. Okay, so as a motivation, so yesterday there was this very funny slide from Jun Kono's talk, and there was this idea of how strong your light matter coupling is. So strong, ultra strong, deep strong, and so on. I was really very interested in this concept, especially when I saw this deep strong stuff. So this is where your G compared to your omega naught. So G is larger than your omega naught. So then I started to think what this means in the context of Fourier engineering and also cavity physics. So here I have this Fourier physics and QED, maybe. So in QED, we have these photons propagating in our systems. So I'm basically talking about the cavities which has continuous waves, so maybe larger cavities. So you have a plane wave and these creation and annihilation operators. When you pump one of these states and create a coherent driving, you get these kind of waves propagating in your system. Okay, so the idea of these strong and deep strong coupling, it actually really exists in these two setups. So for example, as we already know, so this strong coupling is necessary to do topological band engineering in the Fourier language, because we want our strength of the laser to be larger than the dissipation. And we also want this so-called high frequency or relatively higher frequency in this kind of band engineering. In the case of, this is also true in the case of this cavity-induced topological band engineering. Okay, but then in my talk today, I want to focus on this deep, strong side. So this is where our coupling or the strength of the field is large compared to our frequency. Or in other words, our frequency goes very small. So this, in the language of Fourier physics, it's the small frequency limit, which is a very like a nasty limit if we start from Fourier physics, because our dynamics will approach this adiabatic dynamics. So our external field will be very, very slow. Okay. Also, one question I want to address today is, so in these waves, we have this Q of X. So this finite wave number Q. So what will happen to this adiabatic dynamics when we have finite Q? On the other hand, so in QED, so this omega is this dispersion of the photons, omega Q. But let's say if we like push down the zero momentum photon energy to zero, what will happen? So actually there will be like a long range interaction mediated by the photons, and it can lead to some charge confinement. Okay, so first let me talk about this Fourier side. As a concrete example, I would talk about this three-dimensional Dirac particle in a wave which kind of extends this circularly polarized light. So yeah, this is a three-dimensional Dirac particle, and this gamma is just a 4x4 gamma matrix. If you're not so familiar with these 4x4 gamma matrix, then just imagine this is a Pauli matrix, a 2x2. So this is something like a Dirac electron in graphene, or maybe a wire particle in a three-dimensional material. Then let's try to inject this circularly polarized wave to this electron system. Or the combination can be actually very general. So it doesn't have to be light and electron. It can be acoustic wave or plasmons that we have already heard today. And over here, maybe we can have magnons and so on. Actually, this kind of setup is now become kind of popular or being studied in many theoretical groups. So there are some work in the lattice fermion version, and also, in the continuous fermion as well, meaning that lattice, you have the lattice structure for the fermions. Okay, first of all, let's see what is this deep strong state would mean. So as I already mentioned, so we will start with this propagating wave first. So this is the general situation, but let's take some limits. So in the case of Fourier-Bloch state, so this is because we have this cosine which depends on qx and omega t. So this is periodic both in time and space. So if I have an electronic state in this wave, my state will be a Fourier-Bloch state just by this perturbation. Okay, but then if, for example, if I take the small q limit, so I ignore the spatial modulation, I will reduce to this Fourier problem where I only have this temporal homogeneous driving. There, we know that we can use this Fourier quasi-energy diagrams where this is momentum and this is quasi-energy, and we get this kind of Fourier spectrum. One very important property of this Fourier spectrum is that it has a Brillouin zone structure in the energy direction. So yeah, this dashed line part, this is the Brillouin zone. The spectrum will repeat again and again. The size of this Brillouin zone is given by omega. And if we take the small omega limit, this Brillouin zone will become smaller and smaller. And then, as I mentioned, we approach this adiabatic limit. So actually, we cannot really keep on using this Fourier picture for the small omega limit. It's better to use the real-time picture, and we will have some dynamics and time-dependent Hamiltonian where we have a slow evolution. Actually, already in this adiabatic limit, there are many mysteries and new, theoretically new phenomena. For example, one thing is that so when we are near adiabaticity, the first thing first we will think about the Berry phase. But then the next thing is the tunneling process. So from the adiabatic limit, we start have tunneling. Usually this tunneling is understood by the Landau-Zener formula. And if we look into the Landau-Zener formula, actually there are some geometric corrections. So not just the Berry phase for the wave functions, but also the tunneling probability has some modification from the Berry phase quantity. For example, first Berry noticed that there's a shift vector, or he called it a quantum geometric, actually I forgot. So some geometric factor in this tunneling probability, which is very important when we study circularly polarized driving. Okay, but one important thing is that if we look into these tunneling probabilities, this is written using this F, which is the force or the field. The F is omega times A naught. Okay, so we already see that this is highly non-perturbative in this f function, which is proportional to a naught and omega. So we take small omega limit by fixing f. So this means that we are really in this deep coupling limit. Yeah, deep strong coupling limit. You also notice that if we first take the omega zero limit, we will reduce the Bloch state. So we only have a spatial modulation. But then actually, from that limit, we cannot go to this time-dependent state. So there's some like a singularity between the Bloch state and this adiabatic dynamics. Okay, so the question I want to study or address here is, okay, so in this kind of perturbation with Q and omega, so let's plot Q here and omega here, and let's try to do this driving of due to this wave. So what happens in this phase diagram? Okay, we know that when Q is 0, we have the Fourier physics. If we reduce omega, we will approach this adiabatic limit. So the previous speaker, David, has experimentally saw how you approach this tunneling limit. Okay, then here on this side, we have the Bloch state. And this near adiabatic tunneling limit is somewhere around here. Actually, we also know that there is a very important line in this phase diagram, which is known as the Volkov state. This was already studied in 1935, where he studied the solution of the Dirac equation under propagating electromagnetic wave. Actually, this is like a kind of boring solution. Basically, you can move the rotating frame and just get like a very simple solution. So there's a line here. Okay, so where would this deep, strong state exist in this phase diagram? Okay, so that's the question. So to study this, actually there's the answer, so it's probably somewhere around here. So to study this, we'll develop this Fourier-Bloch theorem. So we want to directly calculate the Fourier spectrum for these kind of propagating waves. I have some equations here, but actually you don't have to look at it. Instead, we have this very intuitive picture. So let's say we have this kind of like a Dirac cone. We call this zero photon sector. And then, yeah, simply we will just shift it upward and downward. And call this the one photon sector and this minus one photon sector. What's a little bit different about this picture is that you see that the shift is not directly upward, but it's tilted. So I have finite omega and finite momentum, so Q, in a shift. Actually, so what I wrote here is like a very small extension of the usual Fourier theorem and Bloch theorem using a four-vector notation. A four-vector notation means that if you see this Q dot x or K dot x, it's written as a combination of like omega t minus K dot x, just as in relativistic theory. So it's like it's a very convenient language to use here, even here. So the important thing is that the wave function again looks very alike to the usual Bloch theorem. The only difference is that I have K dot x, Q dot x, which is this four-vector product, and I have this expansion. Okay, so yeah, this is the result. So using this method, one can calculate the Fourier-Bloch spectrum, so the quasi-energy spectrum against Kx and Ky, and it looks something like this. This is a plot for like finite omega and Q, like let's say omega to 10 and Q 5. You already see some structures. So originally I had a three-dimensional Dirac cone, but now you see these tilted bands. So you see bands are tilted like this. Actually, similar features has been already studied by Yang and his collaborator. Another feature is that we have these emergent wire points. So this green and orange dots, they are the wire points emerging because we're kind of pumping this with circularly polarized waves.
Sorry, Takashi, before you go on. I'm a bit confused. So in principle, we're plotting this as a function of k, quasi-momentum, but now you have a q, which in principle breaks momentum conservation, if you like, or translation invariance. How can you still plot it like this? Or, sorry, I'm a bit confused.
Yeah, so there's a lattice structure. So, okay, so I'll show it later. So there, in one limit, there will be a Brock state. Okay, so, okay, the next thing is that, okay, so here, so this is the Brock state. The next thing is this tilting. So actually, this tilting is very, very suggestive. So in the system that we are thinking about, it's a Dirac fermion. So there's a Lorentz symmetry. So here I try to summarize some Lorentz transformation and its properties. It's really just something that you can learn in a textbook in relativity, like Dirac and Dirac. So what Lorentz transformation does is to kind of mix Q and omega. So our space and time directions are rotated. The rotation is given by this hyperbolic cosine and hyperbolic sines. Yeah, this is a Lorentz transformation. By Lorentz transformations, all the states on these hyperbolic lines are connected. You can map one state to another. The states itself are also transformed by this Lorentz transformation. Okay. Then, so all of these formula are basically very identical to what you can see in a textbook. But the only new thing about this is that we can apply this to this Fourier-Bloch ansatz that I mentioned previously. And from this, I can read out that this relation between the two frames are also given by this Lorentz transformation. Okay, so in the next plot, I'll show you this Fourier diagrams. So in this diagram of omega and q, I have this line for the Volkov state. So this is the situation where my propagating wave is traveling at the speed of the Fermi velocity. If I go up, the states are in the Fourier-like state or time-like states. I will basically get this Fourier spectrum, and it's tilted. So you can recover all the states by just tilting the Fourier spectrum. Down here, in this half of the diagram, all the states are related to the Bloch state. So I would have the Brillouin zone. So this blue shaded region is the first Brillouin zone. Now the Brillouin zone is straight up. So I have repeat my structure in the momentum direction. And this is given by Q. The states here are, again, basically just tilted. And again, so what's happening around this Volkov state or this light-like state here? All the bands are folded infinite times. So many band folding takes place. This is a situation very similar to this supersonic situation. That may sound very crazy, but actually what's happening there is not that strange. So actually all the states around this region, as I mentioned, can be related to this slow dynamics that we have here. So if you look at this picture, it worries you, but actually what's happening is I'm having a very slow near adiabatic dynamics, and you can write down your wave functions based on real-time evolution, and then you just Lorentz transform it to the states up here. Okay. So the last plot was for the gapless massless case, but I can do the same for the gapped case. So starting from a gapped Dirac system, actually I can close the gap. Okay, so this color plot shows the size of the gap. The red it is, the gap is small. So here, up here, I have a gap, but then it becomes smaller and smaller, and at this solid line, the gap disappears. Actually, this is the place where I start to create this Fouquet wire semi-metal. But then if I go down, I have this region near this Volkov state. This is this very troublesome near adiabatic dynamics where we have this deep, strong coupling state. Also, one thing to mention is that around this transition point, I will get a type 2 wire point, which is a tilted wire point. Okay, so that was the first part. The last part is about the QED. So here, what I want to study is a very simple system, like a one-dimensional nanotube trapped in a cavity. Yeah, don't ask me how to trap it in a cavity. So assume that the multi-walls, okay, so when I wrote this paper, I was thinking about this multi-wall nanotubes. So yeah, imagine that those walls behave like a cavity. Please. Yeah. So yeah, let's just assume this here at this point. Actually, there are some experimental thing in a two-dimensional organic material that you can actually trap these, realize these states. What I want to mention here, or focus here, is, okay, so this multiple nanotube, they have this upper like Dirac band and lower Dirac band. The lower Dirac band is occupied, so it's like a valence band, and I have a conduction band. And it's called the gap 2 kappa. So 2 kappa. Kappa is the gap parameter. This is kind of oversimplified. In the actual graph nanotube, we have this flavor. So we have valley and spins and the wrapping of the momentum in the y direction, or this tube direction. We also take that into account. Another question is, okay, so related to this omega that I mentioned. So this is a typical picture of a polariton state. In what I want to, okay, so this is just very schematic. So we have this photon mode and exciton mode. Basically, this exciton modes correspond to electron hole excitations here. Okay, so some of the modes are called bright excitons, some are dark excitons. They have different symmetry. I will explain that later. And these bright excitons will couple to the photons, and there will be a hybridization gap. That's a common picture of this polariton, upper polariton and lower polariton state. We also have this omega naught, so this part. So let's assume that we're going to make this omega naught smaller and smaller. So our photons will become massless, so gapless. So what would happen in that limit? Okay. So the question I want to raise here is, again, the similar question. So what will happen if we are in this deep, strong coupling limit, or when this photon mass goes to 0 in the cavity? Okay, so let's, at the same time, so to make this interesting, let's also try to close the gap of this nanotube. So make this kappa smaller and smaller as well. So when we make kappa small, what's the candidate state? So in the ground state. So of course, one candidate is a Latinger liquid. So it's a 1D system and it's correlated. So it should be a Latinger liquid. Another candidate is this exciton insulator. We have excitons, the gap closed. So maybe there's exciton insulator. And when we have this cavity and there's a small photon mass, another candidate should be this confinement phase. Actually, we think that this already exists at finite kappa. So even when kappa is large, I think charge should be confined if we take this small omega limit. Okay, so I'm going to explain this. If you are lucky and find this state in a nanotube, what would be the smoking gun? Of course, one is that in the confinement phase, there will be no single body excitations. So all the electrons will be trapped. I will explain this later. But an important property is related to these excitons. So these bright and dark excitons. As we lower the kappa, the bright excitons, and they'll both come down. But there will be a lower limit, or a limit for the bright excitons. So there will be, it doesn't go to zero. Yeah, this is the claim. And the second claim is that these dark excitons, they don't couple the photons. They go down as we lower the gap, but they go down in a very strange power law. This is actually known as so if I call m pi as the mass energy of this dark exciton, it will scale as kappa to the 1/2. This is known as the Gelman-Oaks-Renner relation in a system which is confined. Also, yeah, there's some, we can see that these bright excitons have a lower limit, which is given by E squared over VF. Okay, so how about this charge confinement? Actually, it's easy to explain this. If we have this cavity, so it's really just solving the Poisson equation in a one-dimensional system. So if all the electric flux is confined, this will lead to a potential, so electron-electron force or potential, which is x linear. So I would have a linearly a potential going up. This immediately leads to charge confinement. So if I solve the Schrödinger equation with this potential, I would get this parity even, parity odd states, and the series. Actually, this parity even states are the dark excitons, and this odd states are the bright excitons that I mentioned. This is a very naive, crude picture, but yeah, this is very intuitive. What this photon energy, omega naught, will do is to bend down this potential. When I have finite omega naught, this will bend, and that it will become flat at some distance. Okay, so yeah, now I have some theory slide, but it's really about how to treat this system. Let me try to explain it very quickly. So the model I study here is this 1 + 1 dimensional QED model. This is known as the Schwinger model. And the very important point, so it's really like Dirac electron coupled to photons. The very important thing about these systems in 1 + 1D is that it's strongly correlated. So if I try to write the ground state, I would have a vacuum state, and then I would have the quantum fluctuations. I would have like a electron hole bubble popping up infinite times. So this is very hard to treat in 1 + 1D. So there should be we have to use some non-perturbative methods. Actually, there are several methods out there. One is the very famous bosonization technique. Yeah, this is one candidate to use. But here, actually, it gives some very nice intuition that I mentioned later, but it's not so easy to calculate the spectrum using bosonization. This is already a very old technique, already developed in the 70s, like Sidney Coleman's paper is a very good reference in this direction. The method I used in my work is this light front quantization. This was also studied and used by some people in QCD and QED in the 70s. So actually the trick is very easy to explain. It's kind of related to the first topic. So in the ground state, we have many quantum fluctuations. But let's try to do this Lorentz boost, as I mentioned in the first part, and rotate this spectrum by 45 degrees. So now I would have this kind of spectrum. Okay, so the special point about this, okay, first of all, this is now something like a type 1.5 wire cone. Okay, so type 1 is the usual one. Type 2 is this flipped one. 1.5 is something that really stands up like this, and one direction is flat. Thus, yeah, the important point is that there's no fluctuation. It's really like a single band system. And if I put my Fermi energy here at the middle, so there's no upper band that you can create these fluctuations. So in this sense, the ground state is trivial. It's the vacuum. Then from this vacuum, I can try to write my electrons by just putting one hole and one electron on these two bands. And this is my ansatz. And then you can solve this ansatz by solving some equation of motion. It's really just writing down the Schrödinger equation in this notation. Okay, so then I'll show you this results. The left panel is work by Ando. He studied a lot about these electrons in nanotubes. I tried to use all the same parameters that he used. He claims that his theory works very well with experiments, so I really copied his parameters. What's written here is these are electrons, but you see that these are magnetic flux on this side. Actually, it is known that if you pierce a magnetic flux string, that's enough. So it's known that if you pierce a magnetic flux in a nanotube, you can modify its mass. So basically what he's doing by changing the flux is to really changing the gap, which is kappa in my language. So he's turning down the gap like this, and then the electron energy will go down. Here it starts to go up, and here it's down, up. If I do the same calculation, but using this QED with the cavity, what happens is that for the bright electrons and dark electrons, the difference is that, as I mentioned previously, so for bright electrons, the energy, even when my gap is going to zero, my electron energy doesn't really go to zero. Okay, there's a finite gap. The dark electrons, they do go to zero, but you see there's this strange curve, like it doesn't go straight down, it's like a square root. So this m pi is like square root of kappa. Oh, by the way, so in the language of QCD, this bright electron is called eta particle, and this dark electron is called pi particle or pi mesons. So you heard about mesons in QCD. What they correspond to in the language of electrons is that our polaritons or bright electrons are the eta mesons, and the dark electrons correspond to pions. Okay, then so is this surprising? So actually it's not. I think, like, first of all, the eta particle, the energy doesn't go to zero. That if you don't know the physics of polariton, that might seem strange. But actually, we already know that if we have this upper polariton, even if we try to push its energy downward, there's a lower limit because my photons are down here. So this state, upper polariton, will be pushed back by the photon energy down here. That's very natural. Also, in the language of bosonizations, it's a very trivial situation where I have a quadratic boson system where I have phi square. Okay, so this is to summarize. So I try to address this question of what is the deep, strong coupling limit of Fouquet physics and this QED. And in the case of Fouquet physics, it's actually the adiabatic limit and the near adiabatic tunneling physics. which extends to finite Q and omega near this Volkov states. The QED case. So when the photon energy goes to zero, or this photon mass goes to zero, the photons will start to mediate long-range interaction inside a cavity. In 1D, it will completely confine your electrons. In 2 plus 1D, it is known that it's really marginally confined. So you have a logarithmic potential. And it's really at the tip of confinement and non-confinement. Okay, so that's all. Thank you very much.
Thank you, Takashi. Questions, John, first, and then Michael.
Thank you. Just to clarify, so this picture of the flow K and block crossover is for 2 plus 1 dimensional Dirac fermion? Or
yeah, this is for 3-dimensional massive Dirac fermions under some
so 3
weights.
plus 1?
3 plus 1.
Okay.
This calculation is done for 3 plus 1, but I believe that this is really general, like even true for 2 plus 1 or even 1 plus 1.
In the 3 plus 1 case, isn't there chiral anomaly? Or?
Yeah, this wire points are related to chiral anomaly, indeed.
Mm-hmm.
Yeah, the emergence of wire points are related to chiral anomaly. From the wire points, you get a quantum Hall effect. Mm-hmm. That response is anomaly.
Mm-hmm. Thanks.
Thanks, Takashi. So this parallel program, is called What is Particle Theory? So maybe you should tell them as a comment. And coming back to my question earlier, so does this require some kind of like Lorentz invariance of your or it can be done generally? I wasn't confused.
This Lorentz transformation part requires Lorentz okay. So that's a good question. So if you do the same for a parabolic band, then you will not get this. In the parabolic band, we'll have Galilei invariance. So whatever potential you have, you can move to the co-moving frame, and the potential will stop. So if you have parabolic band, you only have Bloch states all the time. You can use Galilei transformation to obtain all the states, but it's always a Bloch state, not a Fock state. Yeah, thank you.
Okay. Yes.
And then, in the lattice, I think they'll be kind of mixed. Really, there'll be different results.
I don't see urgent questions. Yes, yes, please, John.
Just keep your, is there then in following up on that, is there a case where you only get flow K states, no block states? Does this have to do with the matrix structure of the Hamiltonian, or?
That's interesting. So that's a situation where your speed is very, very slow. Like this is given by the speed of your fermions. So if you have like a very flat,
like bilayer graphene, or?
graphene.
Okay.
Yeah, maybe you only have these Fock states. Indeed. Yeah, good.
Thanks.
Okay, I declare the session closed. Let's thank Takashi again.
Thank you very much.
Takashi, sorry.